Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Hello test. Hello test. Okay. Good afternoon again, and welcome everyone to Tah Poe Seminar Series 56 and talk number 2. And today, our speaker is Salvatore, and today he will tell us about Ettore Majorana and the real solutions of the Dirac equation. And please welcome our speaker. Hello, test. Hello, test.
And now you can hear me. No? Okay. I want to say is about the pronunciation of the name of the, for me, the most important physicist, Italian physicist in the history of physics. It was not Fermi, it was Majorana. Majorana, no Majorana. The seminar will be in Italian, but no, I'm changing to, to English. I just want to present first some beautiful things so you can get some idea about Majorana, because many people don't know about Majorana. According to Fermi, Majorana was a genius. You can read here a quote by Fermi. So according to Fermi, Ettore was at the same level of Newton, Galileo, probably Einstein too. I think the same. The program of this seminar is this. I will be considering a fundamental problem inside the relativistic quantum mechanics. It's about the real solution of a wave equation, the Dirac equation. How is possible you can construct real solution for the Dirac equation? Yes, you can. We can do that thing. And Majorana was the first physicist to show this is possible, more than 100 years ago, in fact. So the program of this seminar is an introduction. First, I will be commenting about what did Majorana do, and preliminaries, normally mathematical preliminaries. If you love mathematics, I hope so, you will love all the seminar, all the talk, but especially preliminaries. And then I choose just three trivial or simple problems, not trivial, but simple problems, so you can get ideas about how to create real solution, general real solution with the Dirac equation. I would be considering a particle, Majorana particle rest, simple, Majorana free particle in a big interval, but penetrable. So it's a very common model when you are treating with problems in quantum field theory and classical field theory, and also Majorana particle. We are linear Lorentz scalar potential. We can have a Lorentz potential if we want to describe Majorana particle. And finally, I present some final comments in the talk. I just want to comment a little bit about Majorana. Majorana was born in Sicily. Sicily is an Iceland, beautiful Iceland, the south of Italy. According to what we know, Majorana is missing because probably he committed suicide in the year 1938, but nobody knows. Majorana was a graduate in the La Sapienza, the University of Rome, but he started studies in engineering, as you can see here, in engineering. And then he changed your career to physics, because Fermi was looking for students, important students, brilliant students, interested in physics and mathematics. Majorana in 1929 got a master's degree in physics, the most important title you can receive in this university at that time. And in 1932, he published this paper, Relativistic Theory of Particles with Arbitrary Spin. According to me, this is the most incredible paper by Majorana. I recommend you to read this paper, because Majorana in this paper introduced, for the first time, it was not written, infinite dimensional representations for the Lorentz group. Probably you know, the spinor of Dirac has 4 components. 4 components, and the Dirac used just finite dimensional representation of the Lorentz group. We had 3 Buster, we had 3 rotations. But just 3 rotations are just unitary matrices or unitary transformations. But Majorana was able to create representations in infinite dimensions. So the matrices involving two wave functions in two different frames is a big matrix in infinite dimensions, infinite by infinite matrix. So the components for this wave equation of the wave function is an infinite number of components, and you can describe particles with any kind of spin 0, spin 1.5, spin 1, spin 3/2, etc., etc. In 1933, he worked with Heisenberg in Germany. Majorana published a paper. This paper is an incredibly beautiful paper about nuclear theory, the structure of the nucleus of the atom. And in 1937, he published this famous paper. This is the paper in which Majorana introduced the Majorana particle, the Majorana fermions. This is the paper related to the topic of today. So I'm not considering this paper today. I'm just considering just a part of the paper is the part related to real solution of the Dirac equation. Finally, Majorana published just 9 papers in his life, but Majorana left a lot of notes full of calculus or calculation, incredible calculation. I have all the documents by Majorana, by the way. If you are interested, I can give to you. It's incredibly useful, incredible, beautiful to read. So many notes and classes by Majorana. So I recommend you if you want to know more about Ettore Majorana. Because we are speaking about Dirac, because the Dirac equation is the equation to describe a Majorana particle. At least when we are considering elementary particles, you know. But this quote by Dirac, I knew about this quote many years ago. And I myself can identify about this quote. I think the same of Dirac. I was totally in love with wave equation. And I have been working with wave equations more than 30 years. Almost 30 years. I think it's a really beautiful topic to study. Relativistic wave equations. Looking for beautiful mathematical relations. Maybe don't have any physical meaning at all, but sometimes they do. Yes, I have been able to check. This is absolutely true. Okay, let's start with the seminar today. As you probably know, this is the Dirac equation, the free Dirac equation. In 1937, Majorana posed this question. Can we have spin 1.5 particles that are its own antiparticle? And Majorana note is the gamma matrices here present in the Dirac equation satisfy this condition. Look at this operator. This operator acting on C is equal to this. This is real, this is real, this is real, this is real. But I gamma mu is complex. But if you force this condition, so I gamma mu is a real matrix. In fact, there are 4 matrices in this group 1 dimension. You can convert this operator in a real operator. If this operator is real, you can have real solution of the Dirac equation. That's the point. It's very simple. If an operator is real, and it's just like this, acting on a wave function, it's equal to 0, the solution can be written real, but also can be written complex. For example, the Dirac equation permit that thing, but the Klein-Gordon equation permit that thing too. But the Schrodinger equation doesn't permit that thing. Also, the Fesbach-Wheeler equation doesn't permit that thing. Many wave equation doesn't permit that thing. But this equation permit to have a real operator, and so we can get real solution. This result is valid only when a scalar, Lorentz scalar potential is added. If you add all the kind of potential, you cannot find real solutions for this equation. This is interesting. So the only potential that can act or can interact with a particle, that is a Majorana particle, is just the scalar. You cannot put vectorial. I will be explaining this in just 10 minutes. So Majorana found for the first time these matrices. You can see the paper of 1937, and you can check. The Weyl representation, not all the matrices satisfy this. The Dirac representation, very common, cannot do. The Rebi-Jacqui representation cannot. Just the Dirac, the Majorana representation, is able to put this operator real. And that's an important conclusion. Here it is, the paper. The paper was written in English, in Italian, sorry. Teoria simmetrica dell'elettrone del positrone. But you can read the paper in English and probably in other languages too. If you don't have the paper, I can find the paper for you if you want to read in English. I need to present some remarks first. This particle described by the real solution, we call this Majorana particle after Majorana. And it would be a strictly neutral triple one dimension Fermi. Okay? Unfortunately, until now, no elementary particle spin 1.5 has been identified as Majorana particle. But we have two types of particles, hypothetical particles. Probably they are Majorana particles. Sterile neutrinos. This is a very interesting kind of neutrino because the neutrino is left-handed and the antineutrino is right-handed. But the sterile neutrino, the neutrino is right-handed and the antineutrino is left-handed. And these particles doesn't have any kind of charge, even they don't have electric charge, so they can probably be Majorana particles. But experiment until now don't show this. Experiment don't show this particle until now. Neutralinos appear in SUSY supersymmetric theories. Probably they are also Majorana particles. They are strictly neutral particles. Strictly. Okay? Truly neutral particles. All the charts, color charge, hypercharge, isospin charge would be 0. So the particle is equal to its antiparticle. That's the kind of particle a Majorana particle is. So in a Majorana representation, the equation is the Dirac equation, and you need to put a reality condition because the operator is real. So this is the Majorana condition for in a representation of Majorana. But C asterisk, the complex conjugate, is CC, is the charge conjugate wave function. So if this is true and this is true, C equal to CC is the condition that defines a Majorana particle in any representation. Do you want to describe a Majorana particle? Just impose this condition on the solution of the wave equation. The wave function must be CC necessarily. Not just in the Majorana representation. We can find equation for to describe Majorana particle in other kind of representation. There are many, as you know. For me, it's impossible not to explain these remarks. Are really important if you want to understand good the content. Okay, you just choose the Majorana representation. The solution can be written real. You can have an scalar potential. The solution can be real, but not necessarily are real. I can find solution even when the operator is real. The second remark here is a Majorana particle cannot be described only right in this condition. You can select this condition, but if you don't impose the reality condition, you are getting nothing. You are getting a complex solution problem. I have seen many papers. In these papers, you read, oh, they are using the Majorana condition. They are trying to get real solution for some reason. And no. In fact, they are not writing real solution because they are not imposing explicitly the Majorana condition in the Majorana representation. This is bad, really bad. Obviously, depending on the representation you use, the resulting differential equation change. You change the representation, the equation will change. It could be real system of coupled equation. It could be a complex system of coupled equation. Could also could even be a single complex equation for a single component. There are many different manners to express or to describe this, but obviously they are coming from the Dirac equation with the Majorana condition. Specifically in a Majorana representation in 3+1 dimension, the differential equation is a real system of two coupled equations, of course, for two B speeds you have here. Wait. The operator is real, and the equation you have, the Dirac, the time-dependent Dirac equation must be real system, a real system equation. In I don't know what happened. Oh, okay. In a wave representation, for example, 3 plus 1 dimensions, you can have two covariant equations. So you can use, with two components, you can describe a particle with wave function of two components. You don't need 4 components in 3 plus 1 dimension. And also these two equations are covariant. By the way, what do you think about the massless limit of these two equations? Must be the Weyl equation. In fact, you recovered the Weyl equation. But in contrast, in 1 plus 1 dimension, you have a complex system of complex equations. I have been working in this many times, many times, or some years. You can check. There is a big difference between 3 plus 1 and 1 plus 1 dimension, so you need to be careful. More common before to start with the math. Of course, any of these equations can describe Majorana particle, of course, any of them. You can also describe Majorana particle using another representation. By the way, you find very interesting equations and symmetries inside that. But unfortunately, you read papers and you see, oh, the Majorana equation. What is exactly the Majorana equation? You read this is the Majorana equation. Do you see? You have C here, and you have CC here. CC and C are transformed same way, but under Lorentz transformation. So this equation is Lorentz covariant. This is the Majorana equation for many papers and some books. This is an interesting equation to study, but look the manner that it has, because CC is proportional to C asterisk, which the complex conjugate. This equation has not a Hamiltonian form. It's a difficulty you have. But it's super interesting to study this equation if you want, if you prefer to know. Also, other equation people know, call the equation, the Majorana equation is the equation for particles of any kind of a thing. Yes, you can call also that equation the Majorana equation. By the way, this equation supports this transformation. You can include here a scalar potential. But it's not the only, I have been working in scalar with this equation, but in principle, you can add also the kind of potential. What is described in this equation? Some hypothetical particles. They call these particles Majoranons. Majoranons. It's an hypothetical particle, even today. You can see Majoranons in laboratories or experiments. Okay, let's go to the preliminaries, some mathematics here. This equation you see here is the most general Dirac equation. You see, I'm including here a covariant potential. This is a Clifford number. How many component or potential component the component this potential has? Is S a scalar part? It has a pseudo scalar part and a vectorial part. In 3 plus 1 dimension, you have S, you have W, you have a mu, you have pseudo vector part, and you also have a tensorial part. By the way, the tensorial part is able to describe neutrons. How do you describe? You don't do the minimal coupling to describe a neutron. You need to use a complex, the covariant potential, and just using the tensorial part. The tensorial part. Okay, so you have here four possibilities in 1 plus 1. The equation in 3 plus 1 and 1 plus 1 from here in ahead is exactly the same. But this is the most general equation you can, a Dirac equation you can have in 1 plus 1 dimension. We are working with two components, of course. I introduced this gamma phi, but the reality is not this, it's this. And we have the scalar is S, the vectorial is S, is A, mu, it's trivial. This is the same as always. V is electric potential, A is the vector potential, W is a pseudo scalar. Of course, this equation can be written in Hamiltonian form. The Hamiltonian is this big operator. You see, you have this part, common part, and you have the V, the electric potential. You have the scalar, you have the W, the pseudo, the scalar, Lorentz, and the part, this part, that is square beta. Is the energy operator and is the momentum operator. This operator obviously is formally Hermitian or formally Salvatore. It's trivial because you just need this part is Hermitian, this 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 is Hermitian too. So it's easy to prove that thing. Also, I'm supposing all the components of the Clifford number are real values. There is a beautiful thing in 1 plus 1 dimensions. You can remove the spatial part of the A move. Look, just you can gotch away the A move, removing A. Look, this is the solution, no? See. And then you have another solution here. If you put this transformation and you calculate this thing, this part is an integral of A, you eliminate totally A from the equation. So you don't need to include A in 1 plus 1 dimension if you want. Not just physically. Mathematics is giving to you an answer. Not just because magnetic field, you don't have magnetic field in 1 plus 1 dimension. It's because the mathematics is imposing this condition, and then you can remove by a Gauss transformation the potential spatial part of the potential. Okay, this is the Dirac equation. This is the covariant potential, the Clifford number, big potential. We introduce here the equation for CC, the charge conjugate, and this is the potential, the covariant, but C, look the difference, just putting a C. And the relation between gamma mu and SC is given by this. You know this. This is relativistic quantum, simple relativistic quantum mechanics. It's the manner to define the operation. Okay, you just need to do an explaining here. You can convert the equation for C in equation for CC. Just multiplying, putting identities, multiplying by CC, it's just algebra. And this equation is converted in CC equation. This equation. And you compare this with the other equation, the equation for these quantities. And if you compare this with this, you get the charge conjugate scalar potential is given by this, so it's equal to S. The other chain of sign and the other chain of sign too. This is interesting because it's changing the sign. This is related to the fact A mu depends on charge. This is describing an antiparticle, this is describing a particle. So that's the reason a minus appear here. Physically, you can explain this minus. Now, I use the Majorana condition, and if you do that thing, ZC is equal to C. And what do you get? You get this relation. This is equal to this. Of course, this is equal to this, but it's equal to minus A mu, and so is this. Is equal to this. A mu is equal to 0. And W is also equal to 0. So if you want to impose the Majorana condition on the Dirac equation, you cannot have a pseudo-scalar, you cannot potential, you cannot have vector potential, you just can't have a scalar potential. The same conclusion is get when you can get when you use the 3 plus 1 dimensional Dirac equation, of course. So this is the important equation. This is the Majorana equation if you want to describe Majorana particles. It's just this. You're just putting S. As you can know, if this function is depending on X, S plus MC squared is just like the mass is depending on position. So when you are resolving this, it's like resolve an equation with mass depending on the position of the particle. This is information, common information. This is the manner you describe CC. CC is just given by you. Because the Majorana representation imposed this condition, the reality of I gamma mu, or gamma mu is an purely imaginary matrices, this imposed this. So if this is true, this alpha must be real, and beta must be imaginary, purely imaginary, or I beta is real. So you have a bunch of possibilities here. I choose this. Alpha is sigma x, beta is sigma y. gamma y is this, gamma phi is this. You can immediately check sigma x is real, alpha is real, beta is imaginary. Sigma y, the Pauli matrix, sigma y is imaginary. You know. The Majorana condition in the Majorana representation is just the reality condition. So you immediately know the matrix relating C asterisk and C is equal to the identity matrix. So we are working with this wave function. I don't call this Eskino. 1 plus 1 dimension, you cannot introduce Eskino. The spin concept, of course, the corresponding time-dependent Dirac equation is just this. What do you see here? A real system. Look, I. You can remove I and just remain a real system of equations for phi1 and phi2. Simple, no? So it's true. Using the program by Majorana, you can get an equation absolutely real. Of course, you can have real solution of this equation. You can have also complex solution for this equation. It's obvious, no? Okay, the Majorana, the Hamiltonian of Dirac in this representation is imaginary. You can see here that H is given by this 2 by 2 matrix. It's imaginary. You can remove I, put outside, and it's I by an operator that is real. So I by another operator is an imaginary operator. So H is an imaginary operator. The Hamiltonian operator is an imaginary operator in the Majorana representation. And we have here many beautiful results related to this. Our equation is this equation. You can see here, this is the energy operator. You have A. This is a typical wave equation. Many wave equations have this form. The Feshbach-Wheeler equation has this form, for example. The Dirac equation has this form. The Klein-Gordon equation doesn't have this form because it's second order in time. If you want this equation can be a real solution, this operator must satisfy A equal to minus A asterisk. It's so simple. If you want to get a solution real for this must be true. How a Hamiltonian satisfy this? But the Schrodinger Hamiltonian cannot. Because the Hamiltonian is h squared over 2m, the Nabla square, plus a potential, blah, 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 then this is real. So the Schrodinger equation, depending on time, cannot have, it's something trivial, but cannot have a real solution. Never. Never. By the way, each component of the wave equation, the Dirac equation, satisfy a Klein-Gordon equation. Is this equation? It's interesting to know every component of this wave function satisfy a different equation. You can see there is a factor here, plus 1 and minus 1, and so that's the reason you have two different equations. Also, this is not exactly the equation of Klein-Gordon. It's similar, but it's not the same. So Dirac equation 1 plus 1 dimension when a scalar potential is not given to you, the Klein-Gordon equation in a scalar potential is not given to you that result. And then we have the hot part of the seminar, the hot part of the seminar. What about the solutions of the time-independent wave equation? This is the equation for us in Hamiltonian form, where I will be using this solution. This is a stationary solution, energy, and you put this here, and you convert this equation in this equation. This is the time-independent equation. Comment this. E is a real number. It's a real number because this operator is Hermitian, it's Salvatore, formally. And this is IH, and this is beta. If alpha is real, this is real. And if it's beta is real, this is real, and then the operator is real, and C can be real. So when you impose these conditions, the solution of the time-independent Dirac equation are real. But there are not the same solutions, the same conditions when you impose the Majorana condition. The Majorana condition, the Majorana condition is the alpha must be real and beta must be imaginary, pure or purely imaginary. So these conditions are incompatible with these conditions. What is the conclusion? In a Majorana representation, the solution of the time-dependent equation cannot be real. Never, never. This is a topic not commented in books, not commented in papers. Is you know this thing is you are working with Majorana things. It's an interesting point you have here, but many people don't know. You in the Majorana representation, you can have real solution of the time-dependent equation, but you cannot have real solution for the time-dependent Dirac equation. But there are a surprise here. Look at the equation. And supposing in the demonstration E is different to 0, what about when E is equal to 0? E equal to 0. I can remove I because beta is imaginary pure. So we can do this. We can convert this equation for E equals 0, and this is the equation in that specific case, and you can note alpha is alone. It's not with together with I, but I is in the other side. So how do you obtain real solution for this? When alpha is real and I beta is real. Alpha real, I beta. So this is equal to this. And this is absolutely the same of this. So in the Majorana representation, you can have real solution for the time-dependent Dirac equation. You cannot have real solution for the time-independent real equation when the energy is different to 0. But when the energy is equal to 0, you can have real solution. So the Dirac equation in the Majorana representation with energy equal to 0, all the solutions are real solutions, zero mode solutions. That's the reason many people work with this when they try to impose these ideas in condensed matter system. It's very common to hear about modes, energy zero mode. It's because they know that result. When the energy is 0, the Majorana representation can give us real solution for the time-independent Dirac equation. That's important. And finally, I'm presenting here something probably you didn't know, but the Majorana condition could be C equal to this, but can also be a global phase here. But you can know immediately. You can convert this condition in this condition if you do this transformation. So this phase doesn't have observable effects. But you can play with this in case you want to use for some reason a phase different to 1. But it's a comment I just want to play to put here. But it's important. It could be important in some cases. Okay, let's comment about some simple solutions. Okay, the details you can download all the slides from my website, IF website. If you need to know more details, I'm just trying to present this in a pedagogical way, the most simple way, looking for students interested in the topic. By the way, so you are recognizing how simple it is to get real solutions of this equation. Okay, I put P equals 0, S equals 0. The Dirac equation is just the Dirac equation is this. It's super trivial. The Hamiltonian is a matrix 2 by 2. The operator is bounded, so it's Salvatore 2. I introduced in the Hilbert space this scalar product. You know the scalar product for Dirac wave function in 1+1 dimension, in 2+1 dimension can be written this way. You have an internal scalar product. This is the mathematical details. You can avoid mathematical details. You don't like too much mathematics, in fact. But the fact is, you get immediately the eigenvectors for this equation. Really simple. You have an eigenvalue MC squared, means MC squared. Remember, the Dirac equation can give us energy, negative energy solutions. It's very common. Quantum field theory remove that thing. That's the reason we have quantum field theory. Dirac was practically the creator of quantum field theory, of course, by the way. And then you have the equation this, the equation this. You can resolve this immediately, and you can write this in this way. I put all the solutions in pedagogical terms because U, the spinor U and the spinor V appears normally in quantum field theory is the same quantity. And 0 represents P equals 0. The particle is at rest. But know this result. This wave function with negative energy. This result is key when you try to get solutions to describe a Majorana particle. Well, the other thing is mathematics things. It's just they are orthogonals, they are normalized. In fact, this normalization imposes another normalization on V and U. As you know, we had two manners to do this in relativistic quantum mechanics. I choose just this, and you get normal results, and finally you get this. What is the most general solution of this in time equals 0? Okay, the solution for the solution number 1 or plus, and the solution number 2 like this. This is the most general solution you can have at rest. And these coefficients are complex coefficients. Okay, my student, quantum mechanics student know this is a wave function. You can think about Kets, and then you have a Ket here about basis, two-dimensional basis. This is a two-dimensional space, in fact, Hilbert space. And this must be the square of this, modulus, plus this is equal to 1, trivial. And you impose first the Majorana condition. The Majorana condition imposes some conditions on this. You can do that. You have this. Calculate this. Is the asterisk. If this is equal to this, you get this result. And if you get this result, the coefficient here is not independent. It's not independent because it's practically this asterisk. So this solution at t equals 0 can be written this way. So it's this part plus the complex conjugate. Can you know immediately this must be real? But it's real because I impose explicitly the Majorana condition. This by this is real. This is a real quantity. But the modulus is not equal to 1 because you have the sum, and then this is just 2 times, and then you put 1 over this. So if you want to describe a Majorana particle, this quantity must be 1 over square root of 2. We are using this notation throughout this seminar. What about the state of the system? The state of the system at t equals t. Or we have the evolution operator, it's this normal quantum mechanics if you want, and then you calculate this. No, the operator is real. If the operator is real, cannot change the nature, the real nature of the wave function at t equals 0, because this operator acting on this creates a real wave function. So the unitary operator in this case, describing Majorana particle is real. As expected, Cd is real. Finally, you get the solution, the most general solution for a particle rest describing a Majorana particle is evidently a real wave function. But you can also know this, no? The solution is a real state, general state, is an equal weight superposition of the positive negative energy competition state. So to find this, I use two stationary states. So they are connected because of the Majorana condition. Okay. I think I have more than 30 minutes right now. No? 15? 13 minutes? Okay. Okay, I will be passing fast. If you want to see these in details, you can go to my website and I present a lot of results. This condition for the Hamiltonian has consequence. The mean value of h when the wave function is real is always 0. Always 0. In fact, you can construct a theorem. In value of a formally selecting operator, which also satisfies this, is an imaginary pure, in a real state, always vanishes. This is easy to prove that. When the operator is Hermitian, you have this condition, you know the mean value of A is real, and when you have this condition, the operator is imaginary pure, you have this condition, so the mean value of the operator is A. You can use these ideas in other theories, not just in the Majorana ideas. I want to comment about all the operators, but because of we don't have too much time, we can do an analysis of this, all the operators you use. We in relativistic quantum mechanics, we use many operators. The momentum operator is also zero, the mean value, for the same reasons. It's formally Salvatore is imaginary pure, so it's zero, the mean value of P. The data velocity operator, as you know, is C by alpha in the Majorana representation. It's just this, not negative here, so the mean value of this operator is not zero in the Majorana theory. The classical velocity operator also is not zero, the mean value. You can get the reason for this. So in conclusion, in this case, and approximately when this practically is zero, because we are describing a particle at rest, each component of C satisfies the equation of a harmonic oscillator with frequency this. So it's interesting because it is a harmonic oscillator equation, no? The upper component, the wave function, describe Majorana particle, and the lower component satisfy the harmonic oscillator equation. There are one or two papers written many years ago. They comment about Majorana oscillator. Probably Majorana comment about this object, but we don't have evidence that. I have been researching about this. Majorana probably knew about this result. If you see this Majorana oscillator, it's because of this. It's because of this. Like when you have particle rest, you can have the upper component, the lower component satisfy the harmonic oscillator. Perhaps Majorana knew the result. Oh, this is more complicated. We have just 10 minutes to do that thing, but before. This is a little bit long, really long, because there are many details you can use. I don't know if you present this or present this example. And just two trivial examples. Let's consider this example better. Sorry, if you want to know details about the other case, or you can do that thing. Just check the slides after the seminar if you want. Also, people connected online can do that thing. Okay, I put in here a non-trivial potential. Scalar potential is this one. And I need to resolve this problem. Okay, this problem is perfect to impose the Majorana condition. You can have real solution for this. The operator is a Laffian in this Sobolev space. Okay, this 2 is because 2 components. This 2 is because this W something 2 is L squared. These 2 represent L squared. Every Sobolev space that is WK2 is L squared. And 1 represents the function acting by this operator are in L squared, but also the first derivative. This 1 represents first derivative. So what is that space? It's the set of functions in which the function is L squared. The first derivative, the weak derivative, by the way, is different to the strong derivative. The common derivative is also in L squared, and you can check with this, in this space, this operator is self-adjoint. Okay, you can resolve the problem the same way. You have 3 equations to resolve, eigenvalue equations. You have this for A equals 0. This is different to the other problem because you have a state with energy equal to 0, positive energy and negative energy. You can get the results. As you can see, the solution for the state equals 0 is real. as expected. And also we have the eigenvectors for energy positive and negative energy. We have these two sets here. And n is equal to 1, 2, 3, 4, 5, so on. And we have normalization constant here, and we have this constant MC square of k. So you can resolve the problem. We can resolve the problem. It's not trivial, but it's not difficult to get the solution. You can immediately know that Cn minus is exactly equal to this. Represent the same. Represent the same. Comparing with the solution before. Just taking the complex conjugate of this, here appear plus, nothing here, remove that thing, multiply by -1, and you get this. This is asterisk of this is proportional to this. So it's the same state, the same physical state. And finally, there is another symmetry very common when you have scalar potentials. Here is this one. We have a scalar product, so we have relations or orthogonality, blah, blah, blah. And this is the most general state at t equals 0. The positive energies, the zero energies, the negative energy. The normalization imposes this is really trivial, common, but we have to impose the Majorana condition again. You want to describe real solutions, or you want to describe that. And finally, we obtain this result, and we can again write the solution at t equals 0 this way. You see, this is real, this is real, this is real because this is this plus cc. So it's real, and the restriction is given by this, and finally the state cxt is given by this. If you want to get this state, I recommend you to use. Oh, okay. Of course, you know the operator is unbounded. So you cannot use the Taylor expansion to get the state at t equals 0. Be careful with this. But I propose to use the Cato's formula. The Cato formula is this one. When you have a bounded operator, the Taylor series is extremely good. When you have an unbounded operator and you want to get immediately the state of t equal t, this is the correct manner to get the solution. This is an extension of the definition of the exponential function. You can use this absolutely with confidence, and you get immediately the state. It's beautiful. This is not in papers. You know this, you know operator theory, but I'm commenting just the case. I do that thing. I use this function and Cato expression, and then you get this. I get this thing. It's real, of course. So my goal is to present in this seminar real solution, trivial real solution, or simple real solution. In 3 cases, I just present this most simple and then this. But finally, we have this result. This is the result, the most important result in this procedural scheme of things. Do you want to construct real solution for the time-dependent equation? Yes. Okay. Do this. In a Majorana representation, C is an eigenfunction of H with eigenvalue E. So this is true. C asterisk is an eigenfunction of A with eigenvalue minus E. That's the reason C asterisk, the state CC has energy this minus E. You can prove this immediately. Just do the thing, taking the complex conjugate of this equation, and then you get this equation. You do some change here, and you get this formula. And using the conditions to impose real solution to get, and you get this. This is a beautiful theorem. You don't see this in books. I don't know why. There is an important result. If you have the Dirac equation, time difference, and you use a scalar real potential, you have solution for energy positive, C asterisk is the eigenvector for negative energy, and that's it. This is key if you want to get the solution, the real solution to the problem. Okay, let's follow with the final comment. This is the first comment I put here. And then finally, I think this is the most important idea here. There are many things around this topic, but in just 1 hour, I probably need another seminar, Tah Poe Seminar, to explain the other. And also probably present another topic about the Majorana equation. They call the Majorana equation. And a most beautiful seminar probably would be the seminar related to the Dirac, to the Majorana equation, describing any kind of spin particles. A Majorana particle is its own antiparticle, and you can use this to describe this part. In the Majorana representation, the wave function is not the only representation you have, and the wave function can be written real. The reason is because this operator is real. But be careful. You choose the gamma matrices in the Majorana representation, but you need to impose the Majorana condition, because complex solution can be also obtained. The Dirac equation in the Majorana is a real system of equations. Okay, we can describe Majorana particle if the solutions are real. Finally, I put here the real solution of Dirac equations as just a superposition of solution. You see how to get the solutions, just constructing complex eigenstates, and you create a combination of this complex state to create a real solution. Depending on the representation, you can change the system of equations you have. In Majorana, it's real, but in the other representation, it's not real the solution. So it could be probably more complicated. I recommend to use the wave representation, because the equation is just two components for three one dimensions, and it's covariant. And the massless limit you have, the wave equation is very important to get this equation. It's very common, it's very beautiful to resolve the problem in that. Even because the wave representation is related to the representation of the Lorentz growth. And finally, because we need to resolve the Dirac equation in this scalar, I recommend to use the SUSY-QM formalism. This procedure is the factorization method. If you want to get solution of the time-independent Dirac equation, just apply this formalism or the factorization method. It's extremely easy when you have just a scalar, Lorentz scalar interaction. When you have a vectorial, it's more complicated. But when you have a scalar, it's super easy. So you can start resolving the problem. In other words, you can resolve this equation using SUSY-QM methods. I recommend you to use that thing if you want finally to get real solution on a time-dependent equation. And okay, if you don't have any question, I just have for you, I appreciate your presence here, and also great thanks very much, and grazie di mille per essere qua, and that's it.
Okay, thank you very much for a nice talk. Are there any questions here?
So we start with the Dirac equation, which has all the degree of freedom it has, and we further strip or reduce its degree of freedom.
Yes, exactly. When you use the Majorana condition, you are cutting the risk of freedom, because the wave function, the component are related. That's the reason you can reduce the problem not to two components, just to one in 1 plus 1 dimension. If you use the Dirac representation, you reduce the problem of Majorana just to one equation with one component wave function. Yes, you're right. The Majorana condition simplified the description. Yes, from 4 component in triple 1 dimension, you can reduce to 2 components. Just in plus 1 plus 1 dimension, you can reduce the problem from 2 B-spin or 2 components to just 1 component. Yes, you can do that. Yes.
So when we go from the t plus 1 dimension,
T plus 1. Oh.
in t plus 1 dimension, we still have the property like magnetic field, but when in 1 plus 1 dimension, the property like magnetic field is negligible or disappear.
Yes. In this case, you cannot have a magnetic field in 1 plus 1 dimension. Just study the Maxwell electrodynamics in 1 plus 1 dimension. You can have just Coulomb law if you want. And it's not 1 over R squared. as I comment to you one day, I remember. So in 3 plus 1, you have the possibility. But the most beautiful thing is the equation of Dirac, uh, uh, the most general equation of Dirac is this one. And many people don't know. You want to describe the neutron. Okay, normally people think, oh, we just use the minimal coupling. No. First, the neutron is not a Majorana particle because the neutron and the antineutron are not the same particle. And the second is the description is not via a scalar potential. It's via a tensorial potential. You can get the thing immediately. You study the Clifford number in 3 plus 1 dimension. In that case, you have 1 plus 2 plus 2 plus, 4 plus 4 plus 1 plus 1 plus 6. 16 degrees of freedom for potential. In this case, you have just 4, but you can reduce to 3 because you can apply a Gauss transformation. Yes, absolutely. Yes.
Thank you.
Are there any questions? Please feel free to ask.
I just want to comment something finally. Sorry, Hongwet. Because of time, in the second problem, I connect the result with quantum field theory. It was the part I could not present today. But no problem. You can download every people around the world can download in my website the slides and check that thing. It's beautiful because it's very common. The Majorana field is the most important field in quantum field theory too. Normally people work just like a Dirac field is the most important. Okay, but you got the Dirac field, we have the wave field, we have the Majorana field, and all these fields describing different things, in fact, you want to know. And Majorana has the possibility, in fact, we have the possibility to explain this. Okay, the solution of the time-dependent Dirac equation are real, yes. What's the consequence in quantum field theory? The field, Majorana field, is Hermitian. This is the concept, the mathematical condition for that. You don't need to have Hermitian operators, field operators. The Dirac is not real. But just when you are describing wave equations, in other words, when the classical field is real, the field, the quantum field, is Hermitian. And that's the Majorana field is Hermitian. You can check that thing in books, in papers. That's the only comment, Pong. Thank you for the opportunity.
Okay. Thank you. Maybe just a basic question. I mean, we know that there are like a unitary transformation between like direct representation to var representation. So I believe that would be the same to the Majorana representation, right?
In this case, yes, absolutely.
Okay.
Because this equation is using finite dimensional representation of the Lorentz row. In 3 plus 1 dimension, the 3 rotations, we have the 3 boosters. So we have the matrix being relating the wave function in a frame. And the wave function in a frame just have matrices 4 by 4, 4 by 4 matrices. Think about this. Not all the transformations between these 2 wave functions in 2 different frames connected by Lorentz transformation are unitary. Majorana was the first to create unitary representation in infinite dimension. The paper is incredible because you can do that thing, but you have a price to pay. The wave function has infinite dimension. Not in this equation, is in the other equation. In the other equation.
And can you remind me again about the condition or the environment that it required that only E equals 0 have real solution? I mean, I just don't remember. and you mentioned somewhere that only 0 mode, right, have the real.
General, real solution of the time dependent. But in that same representation, the eigenstates of energy are necessarily complex. But What is the but? When the energy of the state is zero, the Majorana continuum pole is the solution of this can be given. This can be chosen to be given. So when the energy is zero of the state is zero, the Majorana representation is real solution in the Majorana state. And it's like a state, zero energy. This is connected to the famous mode, zero mode. The people working with super lesson matter related to yes. The similarities because particle antiparticle in particular elementary particles is similar to the particle and holes. You can have some material, and that's the reason you can use this interpretation. And in fact, they use this result. I lost the result. They use this result related to zero mode. What is the result? No. Sorry, found it. Oh, here it is. So that's the conclusion I expressed here. It's just you can have the solution of this equation, also real, just when the energy is equal to zero. When the energy is different to zero, never you can obtain real solution in the Majorana representation.
Yes, but you can also impose the real condition at the end to match the right the complex solution to. Is
In this case,
I mean, can you compare this result to the final result that you present the general expression for the real for the not
they can be given. And also, we can write with eigenstates and energy zero. The only number we get energy state real is when the energy is zero. Different energy cannot be negative. Don't think about, oh, Majorana representation is given to you every time real solution. No. It's just when you find those solutions. Boundary condition is our case. But here also, like in the older example, you can write the solution real. So the solution can be chosen to be real. But even when the n is equal to zero, the solution can be written complex.
Are there any questions?
Okay, I want to ask you naively, why do we want a real solution? Yeah, not just for Majorana representation, but yes,
Are particles absolutely neutral? Every kind of charge must be zero. This kind of particle represent particles in which the particle and the antiparticle, its antiparticle, are exactly the same. The neutron is a neutral particle. It's electrically neutral, but it's not a Majorana particle. It cannot be. The pion zero is a Majorana particle because it's absolutely equal. The particle, the pion zero, and the antiparticle is absolutely the same particle. The graviton spin equal to 2, it's an hypothetical particle, but it's a Majorana particle, very probably. But the problem is spin 1.5. We don't see in nature until now spin 1.5 Majorana particle. Why not? The possibility is open. Was opened by Majorana with real solutions. Okay? The real solution of the Dirac equation, because you have a representation, a representation in which you can get this. I proved that thing today here. I checked that thing here. So you can get obviously you can describe Majorana particles with complex solutions. You change the representation, of course, you can do that thing. On which is the host.
Okay. Are there any questions left? Okay. If not, I would like to say thank you to Salvatore again. Thank you for a nice presentation.
Oh,
Okay.
congrats.
Okay, and this will be the end of the seminar. Thank you. Just for your information, next week on Friday, we will have another seminar by our team.